say data scientists?
Statistical data scientists. That's a phrase I learned from our colleagues at the Institute of Statistical Mathematics in Japan. And very important political statement. Because data science is everything, right? Everybody's in it. Every biologist, every engineer.
Well, everybody claims to be a scientist.
You know, anybody that deals with data and brings some kind of scientific thinking to the way to deal with that data. I don't think there is, I mean, I don't have a horse in the race, but in the old days, when computer science became a science, I used to refer to computer science as the science of computers and computing, because a lot of computer science has nothing to do with science and applying computers and computation. So computer science has always had its own stuff. Data science doesn't yet have its own stuff, right? It's the stuff of data science is data, and that's everybody's stuff. So I think it's important that we talk about engineering data science, electrical engineering data science, statistical data science, economic data science. So everybody knows that we all own it. Okay, so should we start? Okay, I'm just going to pick up where I left off yesterday. I'm sure it's all fresh in your memories. Just to make sure, the first 4 or 5 slides will cover the territory that we sort of covered in general. There are a few people here today that I know weren't here yesterday, so some more introductory material will be useful for that too. So, simultaneous dynamic graphical models, simultaneous dynamic conditionally Gaussian, conditionally linear, analytically as tractable as possible, decouplable, scalable computationally, dynamic models. Okay, so the context is driven by an interest in 2 things. With multivariate series being focused and flexible and spending 99.95% of the time in terms of model thinking and development and customization, and then scalable in terms of implementation linearly in the number of series, which is the best you can hope for. So simultaneous dynamic modeling will involve simultaneous models for each of the univariate series. Okay? Each of them will be an individual dynamic linear model with all of the analytics available. So individual series can be analyzed sequentially in the ways we discussed just today. Forward filtering, forecasting, updating, usually standard machinery of Bayesian state-space model. If we can exploit some, at least partial parallelization to do this with many series, that's a good thing too. And then when we come to forecasting the set of series and other things related to the use of the models, we want to make sure that we're faithful to multivariate structure that links the series. Okay? From a holistic point of view, we want coherent predictive distributions for the multivariate series into the future, and to use those in whatever decisions we're making. That'll be a portfolio example in the talk today. Okay? The financial time series will today, as I mentioned yesterday, be 401 dimensions. S&P stock prices on a daily basis. Okay? And we'll be looking at forecasting and portfolios in the same framework as we described yesterday, where there'll be a multivariate model implied by a set of decoupled univariate models. And it'll have some predictive part and some residual part. Of course, we'll be going to the inverse of sigma, the precision matrix, which is the volatility matrix capturing across series relationships and their dynamics over time, as well as the volatility of each individual series. Okay. We'll make some comparisons in the example with traditional models. I mentioned a few buzzwords yesterday. I didn't mention multivariate Garch models and other things like that. Sort of standard models, Bayesian models, non-Bayesian models. state space models and observation-driven models, which are, as you scale, don't go there. They just don't scale. They're too inflexible, inherently inflexible, or in cases like this, they're too flexible, they're so flexible they're impossible to fit. Okay. But we'll make some comparisons, okay? So the same kind of cartoon, a couple of slides to stimulate the thinking behind some various models. I changed the names of the series. I made it FX, put it the wrong way around. I should have had the stocks today and the FX yesterday, because that was the example. So this is the yen, this is the Australian dollar, the British pound, the euro, the Norwegian krona, currencies, and we're looking at data that are exchange rates relative to the US dollar, maybe on a daily basis. And you might have a bag of 25 of these, and some other things that you want. So we want to forecast tomorrow based on data up until today. So I'll start in the same way as I did yesterday by saying, well, let's build a model to forecast the yen fluctuations with yen-specific Japan, US, Asia, North America, predictive variables, lagged values of the yen price, and maybe some of the other currencies that lag. And then some residual, some currencies that lag, such as this example. And then some residual that will model everything else that isn't in the predictive part with some volatility. Okay? And then we'll go down the series. We'll do the same for the Australian dollar, the same for the British pound. And the structure of this modeling exercise so far will just be thinking about how the past and what we have available now at t-1 helps inform modeling for each of the series. Okay? And there's crosstalk potential because the fluctuations in prices of the yen and the Australian dollar and so forth yesterday can all be useful in forecasting some of the other prices tomorrow. Now let's get to the contemporaneous relationships, as we did yesterday, and think about the same ideas that if I were to know the exchange rate of the euro and the Australian dollar tomorrow, that might be useful information to predict the exchange rate for the yen. Okay? I'd like to be able to buy that information now in order to predict the yen tomorrow. Okay? So we'll have contemporaneous coupling implied by putting tomorrow's prices of those two series into the model for the yen. And then I'll go down to the next series, the Australian dollar, and play the same game and say, well, if I know the euro exchange rate tomorrow, and I know the yen exchange rate tomorrow, maybe they would be useful for predicting the Australian dollar. Okay. And I'll build a model on that basis. And then I'll go down the list to all of the other series. The J series has the model from the previous slide in the predictive part. And now I'm going to model contemporaneous relationships by giving each series J a small number of parental predictors, the values of the prices of some of the other currencies that I now identify as simultaneous pairs, SP, rather than the PA we had yesterday. Because as you'll see, I'm going to allow series above series J to be a parental predictor in my model for series J. Okay? So I've got arrows that circle around potentially. So that's the difference with respect to what we had yesterday. We had the constraint that only series below you in the ordering can predict you tomorrow. Okay? So the simultaneous substitution, the notation is SP, J for parents. We'll put the predictive part from the past and the idiosyncratic predictors into a mean, mu, just as a label. We'll put the mu's and the nu's each into their own vectors, okay, to make this a vector matrix notation. Okay. And we will have the same assumption as we had yesterday, that for each individual series, there's a volatility in the corresponding diagonal element of the precision matrix lambda, which is diagonal. And these idiosyncratic components, the nu's, are independent across series. Okay? It's a modeling assumption. So there's nothing different there yesterday in terms of the rest of the specification. The gamma matrix, I go to series J. I say in row J of this big m by n matrix, it's going to be 401 by 401. For that series J, identify the columns corresponding to the simultaneous parents of series J. Suppose there are 3 of them. Put the relevant gamma numbers in those boxes, in those row column boxes, and leave everything else 0. Okay? So it's a big, sparse matrix. And it has a cartoon. The blue spots are non-zero, the white spots are 0, as yesterday, with the difference that I'm now allowing loops in this diagram with arrows pointing from simultaneous parents to the children. So that means that this is typically going to be asymmetric and not upper triangular. Diagonal, of course, is 0. But there'll be spots below and above depending on where you choose to locate the parents for each series. So that's all. That's the introduction. That's where we got to yesterday with that difference. Everything else is the same. This is the structural form of a multivariate time series model. Structural y is on both sides. We can move y to the left-hand side, get an I minus gamma. We'll invert that and get this expression, the reduced form of the equation, where the predictive parts are now going to be sort of linked up cross series through this matrix. And the precision matrix is of this, no longer Koleski style, of this product form, where the I minus gamma term is generally going to be sparse. Lambda is a diagonal. So it has the structure of a precision matrix in a graphical model. Typically, we'll have zeros representing conditional independencies, but no longer Koleski. So we'll look at dynamic regression, we'll look at the volatility pieces a little bit, as we did yesterday. Well, just the cartoon, let me put it up there. So here's an example. It's the same example as I had yesterday. I just changed the parental structure a little bit to make it non-triangular. And you can see there's a sparsity pattern there that corresponds to series I is conditionally independent of a lot of series given a set of series that are inherited from this simultaneous parental structure. Okay? Where are the zeros, non-zeros in omega, the precision matrix? They are where they are in gamma, plus gamma transpose. Okay. So the parent-children relationship becomes symmetric in the graphical model. And then the moralization term says if there are unmarried, if there are 2 simultaneous parents that are unmarried, i.e. neither is a parent of the other, then marry them. Okay? So that adds some complexity through this little family group exercise. So it's another way of thinking about a richer class of dynamic graphical models. You can see if I happen to choose by accident or by choice a triangular form, I'm back to our talk yesterday. So that's the DDNMs are a special case. Bit of an aside, just to make sure that we understand the difference between this and specifying a joint distribution directly and looking at complete conditional distributions. Okay? So each y can depend on any of the other y's through the simultaneous parents. What this is not doing is saying, I'm going to start with a multivariate normal model and then look at complete conditionals. You could do that, but what happens then is the plus epsilon t for each series, they're dependent across series. Okay? This is a modeling approach that assumes that conditionally they are independent given their volatilities. Okay? It's a direct specification of the model that is very different than the former. Otherwise, simultaneous equation systems have been used in economics and social sciences for decades. Okay? So it really is a standard way of thinking in some fields. As I mentioned, we start with a structural specification. It becomes a reduced form equation. And some people might say, well, look, you've got all of these gammas in that matrix omega. But omega is a product of 2 terms involving gamma. So the parameters, the numbers in gamma, in omega come from gamma. Well, do you have identification problems? Do you have too many parameters in gamma? And the answer is yes, you can. And you can count parameters. We're in m dimensions, so omega is m by m. And we've got m individual models with their gammas. And if you have the average size of the simultaneous parameter set less than basically m over 2 when n gets big, then you have fewer parameters in this model than there are free parameters in a positive definite symmetric matrix. Okay? So with n non-trivial, you're going to be in this world. Because typically, think about the example, you don't want 50 or 60 FX series, commodities, and other things to predict the yen fluctuations. You've already got a lot of yen-specific stuff going on. What you're interested in is capturing residual volatility patterns that the other series can contribute. So typically, the size of these sets will be small. And it's a modeling strategy that allows you to focus on the gammas, the choice of the simultaneous parents, what the priors are for them, how they may change in time, specifically targeting each series. Okay, so prior information is very important, gets in there. Okay. Mathematically, if you violate this constraint, if you have lots of simultaneous parents, if you have a 10 by 10 matrix and each series has 8 or 9 parents, you've got more gamma, you've got more parameters than are free in omega. And you might care about that. If you're an economist and you want to build a model like this and interpret the gammas from the point of view of causality and economic intervention potential, then you probably want to worry about that. If what you're doing is building a model to capture fluctuations in volatility and co-volatilities for prediction and decisions, you don't care. And the priors drive the utility of that way of thinking, the structure of the model for gammas. Okay? Well, I've just said that out loud. Okay. So to summarize then, we've got a set of DLMs where the F vector, the dynamic regression, the stuff that's got to be known today to predict tomorrow, it's got to be filled in somehow today to predict tomorrow. There's the stuff that is idiosyncratic, the X vector, and then the set of the vector Y indexed by simultaneous parents, this little vector of simultaneous parents for the series. The state vector is correspondingly partitioned. And as it stands, we can use the Bayesian machinery of DLMs to run these models in parallel. For the volatility, I didn't get into details on this. Stochastic volatility model couples in to that analysis of the univariate models. Okay, mentioned this already, that the DDNMs are a special case. Just happened to be interesting to use simultaneous parents where it happened to give a triangular form. And then we run into that question. If that's the order of the series you like, you're in good shape. Okay? And sometimes you can specify a simultaneous system which has some blue spots downstairs, and then reorder them to get a triangular system. And that's nice if that happens. Typically, that won't happen. So why is this interesting? Because remember, the triangular form means that the set of univariate equations define the joint distribution for the YT vector, conditional on everything on the right-hand side, in compositional form. The joint density of Y, given everything else, breaks down into a product of univariate densities. And therefore, the contribution to the likelihood function for the states and volatilities arises as standard normal inverse gamma sort of forms. That's not true in general. Okay? So let's have a little bit more notation. I'm just creating a big theta, a cap theta here, to contain the state vectors of each of the series corresponding to the cap lambda which contains their volatilities. Just to make this expression a bit cleaner. Okay. So what I have here is the density. It's a multivariate model, conditional on everything that I'm conditioning on, which includes all the Fs, all the known information. Each of the series is a conditional Gaussian, and that's what I have there. Product over the series. But when you look at the reduced form of this set of equations, you realize there's a complication. I'll call it an endogeneity factor when I'm talking to economists. Okay? It's a complication that arises because of the fact that the specification of the model with these arrows pointing from simultaneous parents to children creates not a directed acyclic graph, but generally a directed cyclic graph. I like the yen to predict the Australian dollar. Really important series. If I know tomorrow's price of the yen and how it's changed from today, I believe that will be useful to predict fluctuations, the change in the price of the Australian dollar, and vice versa. So I want circularity. And the price you pay, theoretically, is that you no longer have a multivariate normal that factorizes, well, you have a multivariate normal that factorizes, but when you write it all down and you include all of its parameters, this term arises, the positive, this is the absolute value of the determinant of this matrix. So that as a likelihood function for all of the states and volatilities, the piece of the states that comes through the gammas, the simultaneous parental coefficients, enters in a complicated way. So you've got 400 dimensions here, and you've got some specified pattern of non-zeros, and on those blue spots there are some numbers. Let's suppose there are, I don't know, 1,100 of them. So the likelihood function over the state at time t, the contribution to the likelihood function in the gamma dimension, those 1,100 dimensions, is not going to be amenable to a standard normal theory analysis. It screws things up. So the series are almost decoupled. They're decoupled in y's, but the likelihood is coupled across series in this way. And this gives us a bit of a challenge in the analysis. We can't just run standard Bayesian extensions of common fields. Let me just go back to the slide. I say it's almost decoupled, so let's dig into that. Why do I say that? So gamma is this matrix, zeros down the diagonal, lots of zeros off diagonal. As it gets sparser and sparser, it's getting closer and this is getting closer and closer to the edges. Okay. If you've got a 400-dimensional system and there's only one or two parents each, okay, and it's very, very, very sparse. Often you can reorder the rows, reorder the series to create a picture. I don't have that in the slide, where there's some stuff like this in the top, but the rest is triangle. And in those cases, this determinant breaks down into the determinant just in the top corner. And there's some theory, some of you may know, a bit of linear algebra, sparse matrices, hill coefficients, how determinants of matrices like this move towards 1 as this gets sparser. So there's a little bit of theory. It's not very constructive, but it's useful to know. So the idea is that in practicable models with LL sparsity, and this function, this I minus gamma determinant, will be sort of near 1, above 1, or below 1, but it won't be massively fluctuating. Okay. So back to the slide, as a contribution to the likelihood function, well, the gammas are in here. Okay. The gammas are in here, and the observations here are defining the primary information on the gammas, series by series. Of course, there's a prior from the past on each gamma. So that's going to be most of the likelihood contribution in terms of learning for gamma. And of course, for the other parameters, for phi and volatilities, they don't appear. All right. Okay. So this is sort of part of the basis, just the reasoning and the intuition that says, well, let's decouple and run the standard analytics on each series, because that's going to be almost correct in these cases. And then let's figure out how to deal with a correction to make it correct, okay, or to make it closer to correct. And there's a nice coupling of the decouple recouple strategy ideas with two analysis ingredients that do this. One is importance sampling, and one is I'll call it variational base. It's actually doing variational base correctly compared to, some of you will know about variational base, some don't. Most variational base is done incorrectly, and we can talk about that offline. We actually do it correctly, but still it's important. Somebody invented this word, Michael Jordan actually. And I remember talking to him and I said, look, well, we and many others have been doing that for decades. We call it approximation. And I said, I told you the story about naming things yesterday. So let's first talk about forecasting. In the decoupled states, this is the same as DD and Ms. We're at time t minus 1. We want to forecast day t plus 1, day t plus 2. So from each of the series, we generate the state vectors and volatilities, just moving ahead in time. And then at t equals at time t, we'll then recouple the mu vector and the omega matrix. They're just functions of the states across the series. So if you're simulating, you get them trivially. And then conditional on those states, those reduced form parameters, you forecast yt by simulation. And you go to time t plus 1. From the simulated states and volatilities at time t, you get the states and volatilities at t plus 1, and then you get y at t plus 1. Okay? So forecasting doesn't change, so long as you like direct simulation. So now let's talk about the update and the use of importance sampling. I've got about 30 slides in the appendix here with lots of details for anybody that's interested. I'm just going to highlight it this morning. So we've come through forward filtering one step from t minus 1 to t in each of these separate DLMs. So each of them has a conditional conjugate analysis, normal inverse gamma distributions for the states and volatilities by each series. Then we see yt. Okay, we've got to update to the joint posterior of the full set of states and volatilities. And I just told you that the likelihood function has a product of the DLM normals from each observation multiplied by this determinant factor. Therefore, the posterior, since the priors have the conjugate forms, they are conjugate to that product of terms in the likelihood from yt. Okay, so that's a set of decoupled normal inverse gamma distributions. And if we had a triangular system, we'd be done. That's exact. So we do that and say, well, how do we now deal with this component? This is where we introduce importance sampling. From each of those decoupled posteriors, which we're expecting to be almost exact in very sparse problems, that's almost the posterior, and we've got a complicating factor in some lower dimensional part of the parameter space. For those of you that know about importance sampling, you'll know. For those of you that don't, let me tell you, this is a canonical example of when importance sampling works. You want to simulate the joint posterior, and you've got a different distribution because density is almost right. It's a very good approximation. And the exact posterior is it multiplied by some term that doesn't vary very much. Okay, so you simulate from the almost correct distribution. On each of the simulated states and volatilities from the normal inverse gamma distributions here, you pull out the values simulated in the gamma dimension, you evaluate that determinant, and that gives you a positive number. And they, when you normalize them, become the importance sampling weights. So the posterior at that time, the full joint posterior, is represented by a Monte Carlo sample in the space of theta and lambda with a set of weights. It's a discrete approximation to the posterior. Standard importance sampling. So if you want to then make inferences about trajectories of thetas and lambdas and things like that over time, then that's what you use. That's the full joint posterior. You can improve the importance sampling in various ways, very trivially. Most people don't know. If you're interested in projecting down into margins of the distribution, that's something we can talk about if anybody's interested too. Okay, so we got a simulation-based full posterior for inference if we want to. Okay. And if you want to look back over time and do smoothing, that can be fed by this approach as well. Okay. So what we've done there is we've done the prior to posterior update part of the evolve, forecast, and update. But what we haven't done yet is move t from time t to t plus 1. And to do that, we've got to be back in the circumstance where the states and volatilities are decoupled across series, so that we can then evolve to the next time point and predict in a decoupled format. So we've now got to decouple. This is the recoupling. We've got the full posterior. We've now got, before we evolve to the next day, we've got to decouple back to conjugate form posteriors by each series. So let's see how we do that. This is where we do correct variational base. What does variational base do? It says, oh, you've got a distribution, and you want to approximate it with a distribution in a particular parametric family. The mean field variational base approximation to a joint distribution has that parametric family structured in terms of a product of independent terms. Okay. For us, we've got 400 series, and we've got states and volatilities in each series. And what we want is a conjugate normal inverse gamma distribution for each of those series. And we want them independent because we want to decouple. Okay, so a mean field variational base says choose the parameters of each of those normal inverse gamma distributions to match the true posterior, okay, according to some metric. And variational base is always based on Kullback-Leibler. And because we know that the posterior, now represented in terms of important sample, is almost a product of normal inverse gammas, we know this is going to be a pretty good approximation. As an aside, the way most people in the computer science Bayesian statistics community do variational base is they use Kullback-Leibler the wrong way around. Okay? And they do that for a good reason. In many problems, you can do calculations. And that's why. That's from the very start of variational base. If you do Kullback-Leibler the right way around, it's often harder to do the calculations. But if the distribution you're approximating happens to be a Monte Carlo sample, an important sample, for example, or a random sample, you can trivially do Kullback-Leibler minimization the right way. Okay. So this happens to be just a perfect example of that. Okay? So from this important sampling, you've got a million samples. They're almost independent. In the thetas and lambdas that basically are conditional on the gammas. And the gammas are little complicating factors. So you do that calculation. The important sampling, I said this I minus gamma term in good context will be close to 1. So the weights will all be fairly uniform. If you're doing this and at some time you see that that's starting to break down, then worry. Something's changed. Okay? I mentioned yesterday in the poster session to some students that when you do an analysis of this kind, you can relate the actual value of the Kullback-Leibler when you minimize it, its entropy, right, relative entropy, to standard measures of efficacy of important sampling. It's not quite 1:1, but it's a really useful practical guide. The effective sample size, some of you will know that. Important sampling weights, if we call them W1 to W a million, they're probabilities, they add up to 1. The reciprocal of the sum of their squared values is the usual measure of effective sample size. It will be a million when they are all, when the weights are uniform, and when the weights are very variable, it will be lower. So it's standard sort of monitoring idea to look at effective sample size in terms of the efficacy of important sampling. And it gives you a relationship with the entropy in the Kullback-Leibler minimization. Just a beautiful relationship, and I'll give you a nice example later on. So we're doing this over time, sequentially every day, decouple, recouple. So every day, we get a Kullback-Leibler number, and we get an effective sample size. And if the Kullback-Leibler goes up, of course the effective sample size goes down. And you can look at that and monitor it. And it's a big multivariate distribution, but decoupling across 400 series, you could look at it by series and correct for the marginalization. Kullback-Leibler is always better. The divergence always reduces in lower dimensions as you marginalize. So you can look at it in lower dimensions. And you can look at it on subsets of series. And I'll talk more about that when we get to the example. Then the final step, now we've decoupled through variational base, we then evolve in the decoupled system one step ahead. And as Kullback-Leibler always goes down when you marginalize, it also always goes down, i.e. the approximation is improved when you move through a convolution. Okay? And the evolution in the state space model is moving the states and volatilities through a convolution. You're adding noise. You're adding noise to the exact, and you're adding noise to the Kullback-Leibler nearest approximation. You're adding the same noise. So we're going to get closer. So there's lots of good things that come out of this analysis that, more general than dynamic linear modeling with multivariate systems, from the point of view of some of the popular methods in statistics, variational base for doing computations, and some less popular. Importance sampling is not really taught very much, I understand, in many departments these days. It's arguably the second most important simulation method that was ever conceived, the first one being direct simulation. And it's consistent with my thing. I don't want to do hard computations anymore. Importance sampling, in cases where it is almost basically guaranteed to work well, is not. It's just epsilon away from direct simulation. Okay, let me. I think I picked up some friends on the plane over here. Like some friends, they hang around too long. Okay, the example. This is 400 stocks in the S&P. We took a series from about 2002 to end of 2013, and we tried to maximize the length of the data stretch, modulo the number of series. So that's a time period where these 400 companies were listed on the S&P, traded every day. S&P is 500 stocks. There's actually 401. The number 401 is the S&P index itself, okay, which is some, not quite mysterious, but some time variable weighted average of the 500 stocks. This is the time period. This wasn't a very extensive study of predictive models. We built it on returns. We used the year of data, and then we ran the analysis over time blindly with no intervention, which of course is silly if you're actually using models for forecasting decisions. But just that's the example. And then we compared a number of models, and I mentioned some of the standard models and a number of utilities for portfolios. So the example I pulled out for here, just a couple of trivial models. Okay, returns are zero mean normal, right? That's what the folklore is. Well, if they were, then we wouldn't make money, and there wouldn't be markets. So we'll take a model which says there's a local level fluctuating for each series. Okay, so this is the phi component of the theta vector for each series. Or we'll take a model which has a short-term predictor, which is just how bad you did yesterday and the day before. We looked at a whole set of models beyond this. I think, let me put this down here. We looked at a whole set of other models in the supplementary material to one of the papers, where we added other predictors into the predicted part of each of the univariate DLMs. But the story doesn't. The story I want to convey today doesn't change. The comparison is with a traditional Wishart DLM. Okay. So time-varying variance matrix, which allows analytic computations with Wishart volatility models. I made a comment yesterday, and we're going to use it again today, and we do use it in this analysis constructively, that Wishart distributions have a degree of freedom, right? Wishart distributions are precision matrices or variance matrices. There's a single number, degree of freedom. It's a positive number. And that represents uncertainty about the matrix. So if it's a 4x4 matrix with 10 degrees of freedom, let's say 500 degrees of freedom, or a 400 by 400 matrix with 500 degrees of freedom, that 500 degrees of freedom is uncertainty about everything in that matrix. So you can see it's a very constraining. That's why it doesn't scale, because you want much more flexibility in modeling, in this case, relationships and how they change in time. But nevertheless, it's still a work. I should have added to this slide. Last time I gave a talk on this, it was in Japan, so I had to put AIC in there. I don't use AIC. Or BIC or DIC or whatever. I've got a new colleague in engineering, a very senior, distinguished electrical engineer who does a bit of filtering stuff, and he is trying to make a claim that he has figured out the gold standard for star IC. He's got a whole new class of them. All right. So this relates to this question about structural learning that is a bit of a hobby horse of mine. We talked quite a bit about yesterday, about how you find models and how you compare and contrast models. So here, one of the dimensions there, one of the choices, is the simultaneous parents. Okay. So you could use lots of them, as I did yesterday, and use some, Bayesian learning, discounted Bayesian learning if you want to. But think about our problem. We've got 400 dimensions. We've got to do this on each series. Each of them has 2 to the 400 possible sets of parents. You ain't going to do it, even if you wanted to. And I don't think you want to. What do we want? Well, we're interested in 5-day-ahead prediction for portfolios. So we want models that do a good job of characterizing multivariate volatility. I want small parental sets. I want useful parental sets. And if I have a set of parental sets that I think have been useful recently and have been doing okay as far as I care in terms of the forecasting and portfolio characteristics, I'm not going to rock the boat. Okay? Good models, I'll stick with good models until I get worried about them. And I'll monitor them, and then maybe I'll run a few in parallel, make a few variations on a thing. But again, this comes back to the most important slide yesterday, goals. What I don't want to do is follow the sort of standard line of thinking that we're about somehow choosing a model or a set of models in some sort of generic statistical sense to represent, quote, reality. Okay? That's not the way we use models. It's not the way we use models in the kinds of contexts that I'm talking about today. I do want to do forecasting. I do want to do good predictions. That's important to me. So I want to make choices, in this case, parental predictors that are useful for forecasting. And I also want to make portfolio decisions. So the arbiters of model choice and how to think about changing a specification of parents, for example, is a blend of forecasting accuracy and decision outcomes. And the example used a sort of very simple and completely ad hoc, but Bayesian decision theory inspired way of looking at this. And it's just hooking into this comment I made that as long as things are working fine, rock the boat. Monitor performance, predictive performance, decision performance, and now and again maybe intervene and change things. Okay? And the method I'll just allude to on the next slide just adaptively did that. Okay? We used the term refresh. And in the analysis, we actually did this at every time, at every day, which you don't want to do in practice. Okay? You want to stick with models that have been useful until somebody says it's not so useful or you realize you could do better. Okay? And I'll come back to this general point of monitoring over time and intervention in the talk this afternoon a little bit. For those of you who are from industry, this is an old term, management by exception. I think it's from back in the 50s or 60s when people started thinking about quantitative monitoring of systems, in things like inventory and manufacturing processes, before Taguchi. So the principle is that if things are okay and within limits that you have defined, then proceed as usual. And if they seem to break those limits, then jump in and do something. Okay. So all of this stuff is a waste of time in these big models. And we can talk more about BMA and lots of models. Kenny Chiro made some comments about this yesterday and alluded to a paper by people at the New York Fed, Domenici Giannoni's group, this big Bayesian econometrics group, and Domenici's recent paper a couple of years ago, whose title was The Illusion of Sparsity. I think he was doing Bayesian model averaging in a big dynamic regression model in econometrics. And because of collinearities in the design spaces, lots of little models are interesting, because they're all very, very similar, predictably, one step ahead. And therefore, every variable gets some reasonable probability of being, quote, relevant. And that's a real limitation of the sort of standard ways of thinking. Okay, so what we do here is we specify a set of parents. We took 10 for each series, probably too many. We overspecified. We call it in the paper the Bayesian hotspot. And what we were doing was simply saying, well, let's look at what we're doing and ask the question: at any time, is there a series? Is there, in this case, a stock a ticker that is not a simultaneous parent of, say, series 1, that seems to be potentially relevant to series 1? And at the same time, in the current set that I've had for a number of days of simultaneous parents for series 1, is there one of those simultaneous parents that seems to have dropped out of being important? So we can drop out and introduce variables if we had some method of doing it. And over time, with that kind of strategy, if there is a series that's not a current parent of a series 1, but looks as though it might be becoming interesting, I have some predictive value that is not explained by the current simultaneous parents, then keep a track on it for a while, and maybe include it in a few days' time if it continues to show that promise. So we call it the hotspot. Variables can come in or come out, and we do it just by using the standard Wishart model, which is an oversmoothing model, but you can do it in small subsets fairly effectively. It's a trivial computation to identify potential variables for inclusion and exclusion. Okay? This is the start of a whole open area of conversation about challenging research. This conference is supposed to touch on research questions. This is a really open area for the whole area of dynamically modifying, if you like, variables in regressions that are time varying when you've got lots of choices of those variables. That's really what it is. So here's a picture, just of one piece of this. This is the series of the company 3M over our time period of 11 years. Don't worry about the details here. So white means in the row where you see a lot of white, the stock whose name is at the front of that row is not a simultaneous parent of 3M. Where it's red, that stock in that labeling that row is a simultaneous parent. And the horizontal axis is of course time. The yellow is being considered to become a simultaneous parent, or being considered to be dropped out as a simultaneous parent. It's one of those. Don't try and read the names of the series. I don't care about it. These 2 or 3 series were found interesting in the training period, and they hung around. This guy was in there for a while, and then he was dropped out. Somebody else came in. Okay? Presumably highly collinear. Okay. Don't read the names, you don't care about the names. What you care about is short-term predictions, 1 to 5 days, and portfolio returns. Okay? So I can take out a series, let's take out this one, whatever Lusadia National Corporation is, I don't know what that company is, one of the S&P, I can take that out over that period and use this analysis. It would plug in somebody else, a different company. Okay? We're not trying to find and interpret relationships between stocks. You could do that. I mean, you could clearly say for all time, I want to have in the model for Citibank stock, I want to have the Bank of America in the simultaneous parents, and vice versa. Okay, so you could think about sector-specific selection of some of the simultaneous models. So there's a lot of open questions here and open opportunities. So I'm going to just show you a few pictures and summary of the analysis, but one of them is excuse me, just to tie back to the general framework of simultaneous dynamic graphical models. If we had a triangular system of simultaneous parents, that little bit of importance sampling and variational base is not needed. Okay? So this collapses to exact analytics. In general, that's not the case, but it's almost the case, okay, with sparse systems. So you might say, well, if it's almost the case, if your system is sparse enough, maybe 5 parents for each of these series instead of 10, why do it? Why do the importance sampling and the variational base? Because it's almost exact, right? So why worry about it? Well, one answer is because I don't know how exact it is, and that may change over time. Another answer is that even small changes in the numbers in those gamma vectors on simultaneous parallel coefficients, have a role in defining the forecast distributions and the portfolios. Okay, and it's kind of mysterious. It's a complicated determinantal factor how they feed through. So one thing you can look at is things like, well, how does the analysis change if you don't do it? If you pretend it's basically a triangular system, even though you know it's not. So drop that decoupling and just run without it. Use the same code, just comment out that call importance sample, call variation base, and set all the weights to 1. So one way we looked at that and reported in the paper. Oh, you can't see that very well, can you? These are histograms. This is Apple, Bank of America, and General Electric, 3 of the companies. And what the histogram is, it's on 0, 1. So at each time, we'll forecast 1 step ahead with some predicted distribution. It's a large Monte Carlo sample. All right? And do the inverse CDF. Do the calculate CDF of that predicted distribution at the observed value. So the realized value of the ordinate of the CDF. Okay? This is probability 1-on-1. If the data are actually generated from that CDF, that will give you a set of uniform random quantities. The numbers would look like a sample from the uniform. So it's one sequential monitor that's fairly standard in Bayesian forecasting of many to look at things like this. It's a residual plot. Forecast out of sample residual plot. So that should be uniform. That will be uniform if things are perfect. If anybody's ever used univariate volatility models and done this kind of calculation, well, you will always find non-uniformity from simple models, any model, and you tend to find sort of peakedness in the center and fat tails. So if we just ran pretending that without the recoupling step, that's what we would get. You can see these histograms. If you can't see them, I'm just follow my cursor. Are there any cats in the room? So compare that with what you get when we recouple, and these are not perfect uniforms by any stretch. Data wasn't generated from this model, but they're a lot closer to uniform than if you avoid recoupling. So to the portfolios then. Just like yesterday, a collection of portfolios today were lined up, targeting specific target returns, maybe above a benchmark, minimizing risk, the variance of the predicted distribution of the variance of the predicted distribution of the portfolio return, And then there's some benchmark constraints. Let me give you some of the constraints. We incorporated the trading costs into the analysis. So if you were actually seriously interested in trading 401 indices on a daily basis with freedom to buy and sell across all of them, and you weren't behaving like most of us behave, okay? So a lot of people do that with even larger numbers than 400 series, you know, hedge funds and things. Then every trade costs something. They do it because it's basically free for them, but every trade costs us something. So there's some 10 basis points trading costs applied in this analysis to more adequately assess the impact on portfolios, because that's lost money. And the comparisons have half a dozen different portfolios, standard minimum variance, so it will always be the lowest risk, but has no expectation of making money. Target return that's looking at making, on average, 10% over the year, 250 trading days. A more aggressive with about 15% target return. So these are going to be higher risk, obviously. And then the same three strategies, but neutral to the S&P, because you can buy the S&P is in there. Okay? And if you want a portfolio that is going to beat the S&P, you could add another couple of combinations of things, buy some specified target. But this is just looking at, you know, the correlation in the portfolios as you predict them. Okay, your chosen portfolio will be uncorrelated in the predicted distribution, uncorrelated with the prediction with the S&P. And so there are the portfolio. I'm sorry, there are two more there. This is just buying the S&P. This is just the returns on the S&P. This is saying we'll have weight 1 over 401 on each of the series, which is a remarkably robust portfolio strategy. And we'll put those in the bag as well. So we'll put the portfolios along here. And what I have down here is models. So the first models are just local level. So moving just a step away from zero mean returns. The MAs, why do we have 4? 5 versions, some discount factor choices. 5 versions of the MA model, which had a predictive part, which is just basically trying to capture momentum in the prediction based on the last point forecast errors in the last 2 days. Then what I have down here is 3 variants of the Wishart model, which I've mentioned the inflexibility. And the table here could be a number of things. We could put returns or risk or something. This is basically return divided by risk. Standardized measure of return, the Sharpe ratio. So high is good. The S&P is 0.3. The equally weighted average is 0.4. The Wishart models are all beaten by, you know, just buying the S&P. Okay? It's just too constraining in this dimension. Let's not get into the details, just to point out these numbers are all like 0.7 to 0.9. Okay? So doing much better than the Wishart model and doing, you know, twice or more than the naive methods. Okay? So it can help independent of portfolio or model structure. And this is just one example, taking the best Wishart model on one particular portfolio, on all of the portfolios, and the best SGDLM on all of the portfolios to give you a sense of scale in terms of dollars. Again, it's not real life, it's just starting at the 2003 and running blindly over 11 years. Down here we have the S&P as the black line, and the gray line is the equally weighted portfolio. So you put in $1,000 here, and you're up to $3,000 over 11 years. You lost a bit in the recession. You probably would have changed your strategy, as most people should have. Many people didn't. This is with the SGDLM. It suffers the same recessionary effects, of course, but the equally weighted average and the S&P itself are down below now, dominated. And here we are at 3,500. Okay, so So on that metric, the models are an improvement over both standard models and standard strategies. Okay, remind me, about 15 minutes left?
Yes.
Okay, thanks. Time for a drink. We'll come back to the recouple, decouple, specific to the SGDLM strategy. This is just a small value. We use much larger samples than this, but this was an example where we ran it with 5,000 Monte Carlo samples for each important sampling set. On each day, we've got a posterior distribution that is almost the product of conjugate forms across series, almost decoupled. The almost is corrected for by importance sampling, and the effective sample size measures how good that is. If the effective sample size is 5,000, it's perfect. We then realize we've got a triangular system. Okay, or a system that we could make triangular. If that effective sample size comes down to 1,000, we're 20% effective. Something to worry about. If you really want 5,000 samples, and you see an effective sample size of 1,000, then go back and generate an important sample of 25,000, okay, to maintain the effective sample size where you want. So it's not an all or nothing thing. The effective sample size tells you how much you might want to increase your sample to maintain the effective use of that simulation-based analysis to be comparable to an independent, exact simulation analysis. So we have this at every day, and we can monitor these things. Okay, so that comes in the recoupling step, effective sample size. This is about 4,500, 4,200. There's some variation, some fluctuation, and then it's about 45,000 here. There was no change, no intervention, so this was just running blindly. And you can see what happens here. Well, when's this? This is about May 2007. That was the month to buy gold and sell stocks. And then this is later in the recession. So that's a way of thinking about how the important sample is working as you go through time. Okay. And how it deteriorated in times of known change. Down below is correspondingly is the decoupling step, because at each day after we've done the importance sampling and done whatever inference we want to, we then recouple with the variational base. We've got the Kullback-Leibler number that measures how close that approximation is. And I'm just labeling that entropy, it's relative entropy. Okay? And that's what it looks like. So we decouple in red, we recouple in blue. And if you look at those pictures and in your mind turn one of them upside down, you see they're basically the same picture. And when you look at this scale, this is not 0, this is 2 times 10 to the minus 4. This is a big space we're working in. Okay? That's a tiny Kullback-Leibler, but what does it mean? What does that number mean? 2 times 10 to the minus 4. Okay. What it does means relative entropy. It's difference in bits of information. This means something. We've got a 95% effective sample, a 90% effective sample. It dropped down to about a 40% effective sample. So it's a concrete, practicable scale that we can, not exactly, but almost exactly map. When the effective sample size is high and the Kullback-Leibler is low, there's a simple formula that's almost exact. Okay. Effective sample size is roughly 5,000 divided by 1 plus Kullback-Leibler. If Kullback-Leibler is higher and effective sample size is lower, that formula gives an upper bound, not an exact quantity. Okay. So this opens up the opportunity. This is one thing you can look at. You can look at many other things. If you're coming through time and you're in this region, I'm pretty happy with a 90% effective sample size. I might make that 10 or 20,000 or 100,000. But when I say, oh, I suddenly dropped by 10% on the ESS scale, hold on, we've got 12 hours before we have to rebalance our portfolio. We've got plenty of time to think about doing something. Where is it coming from? What's happened? What has changed in the world that I might include in the model now? What might have changed in some structure of the models? Okay. Maybe the banking sector has had some bad news. So some of those stocks, are seeing shifts in relationships with some of the other sectors. Okay, so it provides an opportunity to think about intervention. There's the same plot in red, the Kullback-Leibler entropy, and that's labeled in red. This is Gruber West Financial Stress Index. This is a bit tongue-in-cheek. There are many pictures of this kind that you'll find in all areas all market areas, economics as well as macro as well as finance. And this is arguably the most important and the most well used and regarded. This is the St. Louis Federal Reserve Financial Stress Index. And it's some measure, some weighted average of some bond spread, some bond yields, some spreads, some FX, I can't remember what else. And they change it. I mean, it's their hobby to change it. And it's updated on a weekly basis. And it's good. I mean, it picks up the start of the recession and then the big, well, let me put some things on there. Some of you probably have never heard of Northern Rock. It was a building society that became a bank in the UK, and it was bailed out by the government. Long after the recession was really underway, in August of 2007. I mean, the banking crisis was already well understood, and it was very, very clear. People had been using the too big to fail label phrase for quite a while. So these indices pop up at that time point. Guess what? Ours is a daily index, and it pops up earlier. Here's October 2008, the National Economic Stimulus Act, when the President released many billions of dollars to stimulate the economy, to protect not just the financial sector. For example, clean energy, billions of dollars. Does anybody remember Solara? This came up in a conversation yesterday. $500 million given to some friends. I know one of the people who founded that company. I haven't seen her since then because within 3 months, basically it was clear the company was going nowhere and it vanished, along with $500 million. Major statement that really shocked everything. So it's no surprise that some of the relationships are changing in these series. This is a purely statistical metric. This is just, how good is this posterior approximation? So something has changed in some part of that big space of states and volatilities. And we can create this red curve for any individual stock. It's a marginalization of a pullback-Leibler practice, trivial computation. Or any sector. Some of the sectors cruise through this crisis relative to the banking sector. And then there's a couple of others. This was the ECB response in the so-called Eurozone crisis. And this blip here is more market specific. This is when, was it Moody's dropped the credit rating? Which is kind of a silly thing to do. It's just guaranteed to make a mess of the markets, basically. Anyway, so as a statistical monitor, you can break this red curve into lots of pieces and look at different parts of the model and figure out where the action is coming from when it changes. And that calls for intervention on those components. You don't need to change it. Okay. So that's pretty much it. This is the same slide as yesterday, apart from that I put the word no in there. So DDAMs are a special case. And if you build this model for 400 series and you happen to like triangular systems of parents, and they came out of whatever analysis you did, then run with it. And just comment out the important sampling and variational base. Linearly scalable in numbers of series. The whole business of customization, I don't need to keep repeating. Okay, look at each model, each univariate model, and do your very best for the purposes that you are going to use the overall implied multivariate model. computational scale-up is linear in the number of series. We're building a multivariate volatility model here, in an n by n covariance matrix. But the computations are linear in M. Now we've added a Monte Carlo sample size. Let's suppose it's, I can't use n. Let's use I, capital I for Monte Carlo sample size. So it's linear in that too, because at each time point we've generated an importance zone. That's pretty much it, what I wanted to get to today. This is some of the bottom lines, parallelizable, partially parallelizable, so the decoupled update, forecast, calculations, completely parallelizable. So if you like GPUs, it's nice because then you recouple, okay, and if everything's on the GPU, you then go to the CPU to recouple. Very, very nice for GPUs. And it's a kind of way of thinking that was born for GPUs. And this relates to a theme yesterday in opening. I made some comments about, in the explosion of research in statistics and statistical data science with bigger data, a lot of the machinery that's being produced is pushing hard on the same computational strategies and trying to scale. Okay, not going back to say, well, let's think about changing the modeling strategies in light of what we know we have available computationally. It's a variant on a theme, but it's an important variant. Okay, I'm done. Happy to talk about this. I've got, as I said, about another 30 slides with lots of details and some of the ingredients here, some of which are general, important sampling, variational base, and there's some nice things there of interest in other fields. This is Lutz. He's a Quantco, which is a IT company that works in a variety of areas, insurance, finance in Boston, this in Connecticut. The couple of papers, one is in Bayesian analysis, and the other one's in economics and statistics, and you can find those in the usual place on my website. Okay. With that, thanks for your attention.